Hey friends, we are in chapter 6 and we're talking about ratios, proportions, and similar figures. 6.7, section 6.7 deals specifically with similar figures. What are they? Before we get started, I'd like to just draw a little quick geometric figure like that. All right, not the most beautiful thing in the world, but if I take that, copy it, paste it over here or anywhere, it kind of went where it wanted to go. These figures, even though they're different sizes, or even if they were the same size, see if I can move it. These two figures, this one, these two, if I were to do this, I think I even have the opportunity to do something funky. Let me see if I can rotate it. These figures are called similar figures, and the reason why is because they are the same shape. They might not be the same size and the same shape. So we're going to talk about similar figures. We're going to do a little bit of proportion action on it, and we're going to solve for missing sides. Let's take a look at our vocabulary. So similar figures are figures that have the same shape but not necessarily the same size. And we just discussed that. There's a concept around similar figures that's really important for us, and the idea is the corresponding parts of similar figures. And what those are the sides that are in the same place. Let's go back up to our picture and talk about it really quickly. So here, this side here of my original figure corresponds with this side here. This side in green corresponds with this one because they're in the same place. And yes, I did turn this around, but if we would remember where it was originally, the sides that I'm coloring with light colors are considered corresponding sides. And that's going to be really important for us to make sure that we understand how to solve some of these problems. So corresponding sides are the sides of a similar figure that are in the same position. And then congruent figures are figures whose corresponding sides are the same measure. Basically, if you've got two similar figures and they're exactly the same size, then they're congruent. Let's look at our first example. In example 1, we're going to find the measure of the similar figure, and we're going to basically find the missing side. In this case, the missing side is x because it's the only one labeled with a variable. So what we're going to do here is really set up a proportion based on the fact that, here's the news flash, corresponding sides of similar figures are proportional. So what that means is 4 to 8 is the same as 3 to 6 is the same as x to 4. So I'm going to actually write that down. So from little triangle 4 to 8 big triangle corresponding side is the same as 3 little triangle to 6 corresponding sides again is the same as x is to 4. I know you guys can probably answer this question just by looking at it. Many of you have already realized that the answer is 2, which is cool because it seems like the relationship between the two similar figures is just 1/2. I'm still going to go through the process of doing cross multiplication because I think it's really, really necessary for us to get this skill together. So 3 over 6 is equal to x over 4. I can use any ratio. Since 3 over 6 is closest, I'm going to use that one. I'm going to cross multiply and do my thing. So I get 6x when I multiply these guys together is equal to 12 when I multiply those together. Divide both sides by 6, and we are confirming the fact that x is equal to 2. So this side length would be 2. Let's look at another example. So here in example 2, we have figures that are similar according to what we're told here. I think I took the measures off. Let me put the angle labels back on. Okay, so what we'll see sometimes is just like in our example, the first thing that we did when I kind of flipped it around, what you'll see is sometimes you can have similar figures that are flipped around, and then it's harder to see what sides correspond. So what you want to do is make sure, and you would get a problem that's like this, that has all of the labels on. I had forgotten to put the labels on the vertices, but RST is similar to XYZ, and the motion and the order with which they are named and the motion that I'm going in is going to indicate where the corresponding sides are. So I could also use color to help illustrate this. R is to X, right? And I'm looking at the order here. R is to X as S is to Y as T is to Z. And why is that significant? Because it really does show me that, okay, if I want to compare sides, 3.5 S to R is going to correspond with Y to X or 5. So I'm going to do the problem now. Now I'm going to set up my ratio, set up my two ratios to create a proportion. So small triangle 3.5 to large triangle 5 is equal to small triangle 8.4 to large triangle X. And I know that they correspond. Notice that the vertices are red, blue, so I'm really confident about the corresponding here. So now I can do my cross multiplication, and when I do that, I see that I'm going to set up the equation 3.5 times X is equal to 8.4 times 5. I should use a dot for multiplication. All right, so when I do that, 8.4 times 5 is actually 42. 3.5 is going to stay the same way, and so now I'm going to divide both sides by 3.5 in order to isolate my variable. When I do that, X is actually equal to 12. So what I see is that the length of this side is 12, and so I was able to use similar triangles, or I should actually, since they've given me units, 12 centimeters. X centimeters is 12 centimeters. All right, let's see if we have another example to work on here. All right, so here we have a situation where we have quadrilaterals. Quadrilaterals are just four-sided figures. We could have any kind of sided figure to have similar figures. Oftentimes you'll see triangles though. But here we have quadrilaterals. We can do what we need to do. Find the length of the missing side. The missing side in this case is M. And so we're going to find the length of M. How can we do it? We need to set up proportions. When I looked at this at first, I was like, oh, well, 13 to 13 to what? They didn't give me the side that will correspond to AD in the larger quadrilateral. I have to be careful to not just use what I see, but use what I need to get what I want. And so what I need and what I actually have is this relationship here. DC corresponds to ZY, and I can also tell by these interesting marks here. These marks, when you guys get to geometry, tell you that angle A is equal to angle M, and angle W, and angle B is equal to angle X because of the marks, the number of marks that are indicating each angle. Anyway, back to what we were saying. Side DC corresponds to side ZY. So instead of doing 13, I'm going to do 10, right? So 10, small quadrilateral, 10, small quadrilateral to large quadrilateral 15 is the same as, so I've used what I've got to get what I want. I want M. What corresponds with M? This side CB. So I'm going to say, again, small quadrilateral to large quadrilateral. I'm going to do my cross multiplication and solve this problem. Before we even solve it, I do want you to know that my caveat, or my usage of small triangle to large triangle, or small shape to large shape, is not necessary. You could do large to small, but you just need to be consistent with both ratios. So for instance, I could have had this set up as 15 over 10 is equal to M over 12. That's one way. There's also other ways, but let's calculate this problem. So our work does this, so we're going to multiply 15 times 12. Sorry for not getting that loop right. 15 times 12 is 180. 10 times N is equal to 10M. Then we're going to divide both sides by 10 to isolate our variable, and we get 18. So M is equal to 18, and we're done. So 18 is the answer to this. Our assignment is as follows. Please make sure you let me know if there's anything that's unclear in the video. Ask any questions. Do what of the assignment you can. Try a couple problems, even if you're at home, just to make sure you know what's going on and you can have some good questions for me in class. Can't wait to see you guys tomorrow. Have a great day.